Hi guys, this is Saka, and I'm here to talk to you guys about EM radiation, kind of do like a little review. I'll do a couple other little short ones later going over problems. There is one problem in here that I'll review, but this is just kind of an overview of most of Unit 8. So, we've defined the nucleus, and one of the reasons why we're spending so much time on EM spectrum is because we're ultimately trying to figure out the way electrons are arranged. Why aren't how are the how is the nucleus the centerpiece, and how are the electrons arranged around it, um, and how electrons account for the chemical behavior of elements is something we've also talked a little bit about. And the idea here is that if we understand the arrangement of electrons, we ultimately can understand how atoms combine to form compounds. And we also are looking at the light given off by element as a way to kind of understand this. So the wave nature of light, we've talked about the EM spectrum, and the idea here is that all energy exhibits wave-like behavior as it travels through space in a linear fashion. So the path is linear, but the actual energy will move in a wave-like pattern. And this little slide kind of illustrates this idea. So the idea here is that all EM moves at the speed of light, no matter what. Lambda, we've talked about as wavelength. This is the distance from crest to crest. The A's are amplitude. The nu is frequency. That's how many wave cycles there are per unit time, usually in seconds. And T is a period, the time between successive until a wave cycle begins to repeat itself. So these are just basic properties of waves. A little bit more about the wave nature, and we've talked about this in class, where the speed of light equals the wavelength times the frequency. C, remember, there's a car driving by. C is the speed of light. It moves at 3 times 10 to the 8th meters per second. Remember, lambda is wavelength in meters, and nu is frequency in either hertz or seconds to the -1 or 1 over seconds. They all basically are units of frequency. Doesn't matter, all the EM waves move at the same speed. What differs is their wavelength and frequencies. If we have a low frequency, the wavelength distances are long, whereas if I have a high frequency, the wavelengths are short. We've kind of illustrated this throughout the unit. EM radiation is basically the EM spectrum is all forms of electromagnetic radiation. And so here's a figure that illustrates this. And we've kind of talked about parts of these throughout the unit, where in terms of wavelength, the ones with the greatest wavelength are radio waves, and the ones with the shortest wavelengths are gamma rays. And in terms of frequency, the lowest frequency is the radio, and the highest frequency is the gamma. And then we have our visible spectrum in between. And so we talked about Roy G. Biv in the clicker test today. This is the order from um, uh, low frequency to high frequency, or long wavelength to short wavelength. Okay, here's a sample frequency calculation. So what is the wavelength of a microwave having this frequency in hertz? And so we need to figure out which equation we're going to use, which is C equals lambda times nu. Define our variables. So C is a constant, we'll always have that one. Lambdas are unknown, that's what we're solving for, and nu is 3.44 times 10 to the 9th seconds to the -1. Remember, seconds to the -1 and hertz are the same thing. And then all we have to do is substitute and solve. So we go ahead and plug everything into our equation. We do some fancy algebra, and we end up with 0.872 meters as our wavelength. So not so bad. And I'll do some more calculations like this that are a little bit more challenging shortly in a separate video, because it takes longer to explain those. The particle nature of light. So light does have properties of particles too. They carry energy. And what we find is that heated objects emit only certain frequencies of light. And we've kind of touched on this when we talked about the atomic energy spectrum. This is where the particle idea comes into place here. As I said before, the duality of light, whether it was a particle or a wave, kind of was controversial for physics for a long time. What we find is that some metals emit colored electrons of a specific frequency when a color light of a frequency shines on them. And this is something that's kind of, I'll show you a figure what this looks like in a minute. I know it's kind of confusing. But some metals, if you shine light on them, they give off electrons. Okay? And so the idea here is Einstein's theory of relativity combined with Planck's equation um, illustrate this with the photoelectric effect, which is a phenomenon we haven't really talked about yet, but I'll touch on more in class tomorrow. And so the idea here is that waves or light can behave like a particle too, in the sense that it has energy and energy has mass, and that was kind of the hard part. The quantum concept is the idea, this whole idea of giving off colors when heating things is the whole crux behind that. And we've been calling them photons the whole time, but another way to refer to this in a more general way is to call it a quantum. And this is the minimum amount of energy that can be gained or lost by an atom. This was a big idea back in the early 20th century. It went against classic Newtonian physics. Max Planck, whose equation we've kind of talked about before, showed that objects gain little packets of energy, which we've called photons, in a mathematically repeatable fashion. Okay, and this is our Planck's equation. We know h's are constant. And the idea here is that Planck's equation shows why EM waves have more energy than others. So why purple light causes my glow-in-the-dark paper to glow or to light the match that I showed you guys, while other colors of light aren't capable of that. And so here's the photoelectric effect. I know this is kind of hard to see, but the idea here is photoelectrons are emitted. So here's our metal surface, the thing with the two lines and then minuses here, and when light of a certain frequency shine on the surface, this is what these red squiggly lines are. If it has a high enough frequency or carries enough energy within the light, electrons or photoelectrons will leave the surface. Now the wave model by itself couldn't explain this, and this is why the photoelectric effect is so important. And this is, if you think about it, this is kind of like the original idea behind solar energy. So the idea that you could harness light from the sun to create electricity. Basically the same idea, except now these electrons are carried by a wire to complete a circuit to charge a battery. So Einstein applied Planck's theory to this idea. And a photon, remember, is light energy. And again, the photon equals hv. Again, this is something we've talked about before. If we shine more light, so if there's more red squiggly lines, you'll get more photoelectrons. But if you have a higher frequency of light, I don't know why I put h there, it should be frequency, you get electrons with more energy behind them. Okay? And this proved that light has dual properties, particle and wave-like properties. Something that we've talked about before. The atomic emission spectra is another idea behind Planck's equation, which we did a lab on and we talked a little bit about today. And the idea is that the set of frequencies of the EM waves are emitted by atoms of an element, which we see as light. And each element has its own fingerprint or unique emission spectrum, and this is why only colors of certain frequencies and wavelengths are given off for a particular element. And it's not a continuous series of colors. In other words, each atom will give off a different color. That's possible, and the quantum theory kind of predicts this. We're not going to get into it too deeply, but it does, and if you are brave enough to try AP-Chem, you'll get into this in much more detail. And so this is hydrogen spectrum again. And we've talked a little bit about this in class today. Don't worry about the equation so much, but look at the colored lines here. So the idea here is that electrons will jump from level 2 to higher levels, and as they fall back down to their original level or ground state, these little squiggly lines represent the wavelengths of light given off. Okay. Now, what I didn't talk about, but what also happens, is that you can get jumps to even higher levels from n equals 3 or n equals 1 and back down. But those wavelengths and frequencies cannot be seen by our eyes. So like the series jumping from n equals 1 up and back down are ultraviolet light, and the ones that start at the third level up and back down represent infrared. And those are, remember, we can't see anything other than the visible spectrum. So we can detect them with other instruments, but we can't actually see them, but we could detect them if we needed to. So not only is the color of light unique, but also the UV and infrared frequencies and wavelengths would be unique as well. And that's it for now. See you later.